So taking a look at a sapling acid-base question, this is the key here is the question is basically asking us, do we know what kind of arrows we're going to have here? So we know it's an equilibrium reaction, and so the question is, are the arrows even? Does it lean more this way? Does it lean more towards starting materials and less towards products? So there's 3 options. The way to think about this is to think about electronegativity, essentially, right? So if you remember the types of reactive bases that will work with sp hybridized CHs, you need really reactive bases. OH minus is actually not one of those reactive bases. Those reactive bases were Na, NH2, minus and a plus. So a negatively charged nitrogen. And the other example was butyl lithium, a negatively charged sp3 hybridized at carbon. So carbon the negative charge and nitrogen the negative charge are reactive enough, but actually OH minus is not. So this actually does not favor products. It favors reactants, just based on electronegativity, right? So if you knew something about the types of bases that are needed to get this CH bond to react, you would maybe realize that O minus is not reactive enough because it usually takes N minus or C minus to make that react. Right. So yeah, exactly. So the key here is nitrogen and carbon are not as electronegative, so they're not as stable the negative charges as oxygen would be, right? OH minus is still reactive. It's just not as reactive as N minus or C minus because of electronegativity, right? So question number 5 on the 2017 exam, 3. So this involves a alkene. It's going to react with HCl. And just like anytime you do these addition reactions, you have to think about which carbon will be most stable as a carbocation. So the mechanism would be lone pairs react with the H, break the HCl bond, and we have 2 possibilities for carbocations. We either have a carbocation at carbon 1 or the carbocation, right, if we draw the H's in, of course, draw the H's in. We could have the plus charge on carbon 1, 1, 2, or we could have the plus charge on carbon 2. Which one's better? They're not the same. The first one, right? Why is this one better? Because this can do lone pair resonance. All right, I can do lone pair resonance. Cl minus can then come in from the top or the bottom, doesn't matter. And that gets us to the most stable product that comes from the most stable intermediate. One, 2, lone pairs, lone pairs. Chlorine looks a little ugly. All right, and it could be Cl could be wedged or hatched, so you get both enantiomers there because you made an asymmetric center at carbon 1. So this would be the most stable product because most likely product, most stable product because it comes from the most stable intermediate over here that's stabilized by lone pair resonance. So this is another one, number 5 or number 4, depends on which test you're on from 2017. And this one involves working backwards. We got to figure out what the starting material was. So the product here is an alkyne. And what we have here is reagents is a strong base. 2 equivalents is a strong base. So how many ways do you know how to make an alkyne? You literally only know 1. To make a terminal alkyne. Literally only know, well, you know 2 ways. You can do the deprotonation to add stuff, or you do the double E2 to make 2 pi bonds. Do 2 eliminations, you get 2 pi bonds. So let's number our carbons. 1, 2, 3, 4, 5, 6. So we know between carbon 1 and carbon 2, we need to make 2 pi bonds, right? So we have to do an alkyne synthesis. So if there's carbon 1 and carbon 2, What do we need to put either on one of those or on both of those to get pi bonds? We need to put leaving groups on there, right? So there's a couple ways you could do this. You could put one on, or you could put a bromine on 2 and put a bromine on 1. That'd work. Or you could do, let's see, you could put 2 bromines on 2. Or you could have put 2 bromines on 1. All right, either way, you got to do a double E2, right, to get to there. So you need to do a double E2. You need 2 leaving groups, no matter what. So that's what you need to think about. Right. So the difficult part here is to recognize, right? I have an alkyne. How many ways do you know how to make alkynes? Think about the way, like think about the products here. Make an alkyne. You literally only know 2 ways.
Is this like the peri? So that
It has to be everything has to be anti-periplanar, but you're not being asked that here. But yeah, of course, yes. In E2 reaction, things need to be anti-periplanar both ways. But that would work. 2 leaving groups, 2 pi bonds. Alkane to alkyne. Means if you look back, what the heck just happened? Oh, shoot. So let's try an example of that retrosynthesis working backwards. So what you can see here, we have an aldehyde, and here we have a alkane with 2 bromines on it. We have an aldehyde, right? So let's just take a second and think about what's changed, what's different. So let's number the carbons on the product. So there's 4 carbons on the product. How many carbons are in the starting material? 2. So we know we need to add 2 C's. How many ways do you know how to add carbons?
1.
Just that 1. So we know we're going to need NaNH2. To deprotonate, we're going to need a terminal alkyne. All right, terminal alkyne. That there. What else do we know about this? We have an aldehyde. Where do aldehydes come from? What kind of reactions make aldehydes? Oxidations. What's that? What was the name of the reaction? Maybe a hydroboration of what? What do you do a hydroboration of to get an aldehyde? Hydroboration of, well, what starting material do you react with BH3 to get an aldehyde? So chapter 12 is about alkenes. Chapter 13 is about alkynes. It's one of those 2 things. We've made aldehydes. There's one way to make an aldehyde. Not hydroboration of a alkyne, right? BH3 plus an alkyne will get you to a ketone right after the or aldehyde after the tautomerization, right? Getting even farther back, there's 2 bromines. What can I do with that? If I know I need to get a terminal alkyne, can I turn this into an alkyne? What do I need to do? 2 E2 reactions. Right? All right, so one step back, that aldehyde came from one step back, it was a enol. All right, that's cis addition. Number of our carbons, 1, 2, 3, 4. One more step back from that enol came from what? An alkyne. Between which 2 carbons? 1 and 2. One, 2, 3, 4. That alkyne, right, all of a sudden has 4 carbons. What alkyne did that come from? It came from this alkyne, 1 and 2. And where did that alkyne come from? It came from the double elimination of that of those 2 leaving groups. So now if you start working forward, so that means this was carbon 1 and this was carbon 2. So if you start working forward now, you need Na, NH2, at least two equivalences of that. That gets you to an alkyne. If you want to add carbons, step 1 is Na, NH2. That would deprotonate carbon 2. And then we're going to add in one equivalent. Right, we need to add 2 carbons. So we're adding an ethyl bromide. That would be carbon 3 and 4. Do an SN2 there. So it doesn't have to be NaH2. You could also use the butyl lithium. Any strong base. N- or C-. That gets you here. Now if we want to do a hydroboration, we need BH3, then H2O2, OH-. That'll give us an enol first. The syn enol, right? The H and the boron, H and the oxygen on the same side, and the anti-Markovnikov addition. And then following Tautomerization, we get to the aldehyde. So these problems are certainly challenging, but the key is laying out this plan. Being able to look at it and say, I need to add carbons. Oh, that means I need to use NaNH2 or a strong base, right? I need to add 2 carbons, so I know I need to add something like this. I have a hydroboration because I get an aldehyde. You recognize an aldehyde comes from an enol that was an anti-Markovnikov enol. That enol came from a terminal alkyne reacting with BH3, right? So just kind of seeing all these things and working your way back to it. So one of the challenging steps, you have to recognize to get to an aldehyde, you had to use an alkyne, right? So that means if you look back, right, if I see this, I know I had to recognize there has to be an alkyne. That means I need to turn this starting material at some point into an alkyne. I see 2 leaving groups. Every time I do an elimination, I get 1 pi bond. If there's 2 bromines, I can get 2 pi bonds, which gets me to an alkyne. So it's kind of just recognizing I only know one way to make aldehydes, and that's through the hydroboration of an alkyne. I know I need to make an alkyne, so I need to turn this into an alkyne somehow. And you only know one way to make alkynes, this double E2. I knew it was hydroboration because it's an aldehyde. I only know one way to make an aldehyde, and that's through an anti-Markovnikov addition to a terminal alkyne. You only know one way to make an aldehyde. It's the only way you know how.
What about
If it was mercury here, you would have got a ketone, right? Because you did a Markovnikov addition and got a trans enol. All right, so you only know one way to make an aldehyde. So if you see an aldehyde, this is it. Terminal alkyne and hydroboration. Right, just like you only know one way to make an alkyne is double elimination. You only know one way to add carbons to an alkyne. Strong base, SN2. Right, so you start to see this stuff. You don't really have that many options to do these things. So this is a practice one. This is from Sapling, homework number 8. So this kind of takes you through. It wants you to kind of show the steps in an oxymercuation. So the first step, of course, the pi bond reacts, the lone pair comes back, and we get that syn addition. And it's hard to see with some of these sometimes, but you can see Hg2+. So the mercury adds. It adds on all in one face. And so it asks for the first neutral products. This is actually the first... Actually, no, this is not. So then you get to here, and we have carbon 1 and 2, and there's water in the system. So the next step is the solvent reacts. So which carbon is going to react with carbon 1 or carbon 2? Carbon 1, Markovnikov addition, right? Always Markovnikov, the more substituted one. So it's going to react with 1. That's going to break that. So it's like an SN2, right, reaction. So now, right, the methyl is now up. We just added the water, right, to the back side. The mercury would be here. Now it's 1+. And we have an H. So carbon 1 and carbon 2, right? Mercury get that trans the things on opposite sides. And what the question asks for is the neutral product. So another water would come around and take off that H. So the one of the products would be an OH, and the mercury, mercury would be up, and then the hatch H. Biggest things to take away: the oxygen, the OH that added, the solvent that added, is on opposite side, is trans to the mercury. So this is the first step. This is the neutral product of that first step. And then that's what you need to know the mechanism for. And then the last step, all it is they add in NaBH4. And you don't need to know. And also they add in NaBH4 and OH minus. All you do is replace the mercury with an OH. Or an H, excuse me, sorry, good call. NH. Yep, NH. With an H. So there's two H's there, carbon 1 and carbon 2. So that's what the final product would be.
So we would have to know the last.
You need to know these reagents, right? Usually it's step 1 and then step 2. You'll see that written like that. You do not need to know the mechanism for this. Right, you need to know all this stuff I showed you the mechanism for. So what sapling does want, so ask yourself, you finished, you said, do I have any asymmetric centers? Did I make any asymmetric centers here? No. Right, it's two H's. There's no asymmetric center here. But now going back one step though, I do have asymmetric centers here. Right, both of these are asymmetric centers. That's sp3 hybridized bond to 4 different things. So I need to draw the enantiomer of this as well. So sapling wants the enantiomer of this as well. And so that's easy enough to draw. So the mercury would be down, the OH would be up, and there'd be an H there, right? So these are enantiomers to each other. But sapling did want both of those. And that thing to me, that's the point of the confusion. So let's do an alkyne hydration quick, or alkyne hydrohalogenation, and alkyne hydrohalogenation. Or actually, let's take it a step further. Let's say it's in water. So HCl and water. So the first step, number of carbons. Pi bond reacts with HCl. We need to make a carbocation. Which carbon do you want to put a plus charge on? 2. And we'd like to make it trans to whatever we added, just so you remember that. So if I said this was HA and this is HB, this would be HA and this would be HB. The carbocation is kind of opposite the hydrogen that adds. So we also made Cl minus. And Cl minus is of course more reactive than water, but there's a lot of water around. So that's just going to react instead. So now you have that you have that enol-ish kind of thing, plus charge on the oxygen. 1, 2, 3. 1, 2, 3. Cl minus still floating around, right? You could do a quick tautomerization if you wanted to. That would get you to this ketone. 1, 2, 3. And then at the last step, Cl minus could come in and take that H and regenerate HCl. So HCl in this case would be a catalyst. And then it'll get you to a ketone. Right? It's a hydration reaction essentially. HCl and water, or H plus and water would work too. So it's a hydration, acid catalyzed hydration of an alkyne. So let's take a look back at an ozone reaction. So first thing, so we're going to work backwards to figure out what the starting material is. So first thing you recognize, okay, so ozone. So you know something about ozone, hopefully. And then you recognize that these are both carboxylic acids. So did they come? So what was the starting material? Was it an alkene or an alkyne? Probably an alkyne, right? So we say, okay, alkyne, right? So I know it's an alkyne. Let's number some carbons. 1, 2, 3, 4, 5, 6, 7. Which two carbons were probably bonded together? 1 and 3. Careful. It's the carbon of the carbonyls. 1 and 3 were bonded together. 1 and 3 were bonded together, right? That's where they, right? So make sure we're careful about drawing our alkynes. Get our bond angles right. So carbon 1 and carbon 3, that'd be carbon 2. This would be carbon 4. What else is bonded to carbon 4? 5, 6, and 7. 5, 6, 7. This would be the starting material that made these two products after reacting with O3. Right? You can see that by, right, dividing this down the middle. That's where your two carboxylic acids came from. So carbons 1 and 3 coming together. Careful to draw your alkyne correctly. Draw the alkyne first. Make sure you do the bond angles right. Number your carbons. So what if we switch it around and looked at something like this? So it's a little different. So ozone again, but now we have two aldehydes. Two aldehydes, not carboxylic acids. This should tell you this is probably an alkene starting material. And carbon 1 and carbon 3 are bonded together. So an alkene, 1 and 3, there could be 2. It doesn't matter if it's, you wouldn't know if it's a cis or trans alkene. You wouldn't know that. So 4, 5, 6, 7. So this is a possible alkene reacting with ozone would make these two aldehydes, right? Where this gets spliced down there and makes the two carbonyls.